am Abbas and I am a research assistant at the Department of Computer Vision, Mohammed bin Zayed University of Artificial Intelligence. In this presentation, I will explain my paper titled CamoFocus, Enhancing Camouflage Object Detection with Split Feature Focal Modulation and Context Refinement. So let's take a closer look at camouflage object detection and the proposed techniques. Compared to other types of object detection tasks, detecting camouflage object poses a unique set of challenges to the learning algorithms. For instance, in this figure we have an image which is starting point of our analysis. Then we have generic objects, which are the objects segmented under the standard conditions. And we have salient objects, which are the clearly visible objects in the image. And finally we have camouflage objects, which are seamlessly blended into their surrounding environment. So technically they are quite difficult to segment or detect. The applications of camouflage object detection. It could be used in medical imaging, for instance in polyp segmentation, where the benign region closely resembles with the malignant region, and it could be effectively used to segment that regions. Similarly, it can be used in surveillance and security. Afterwards, it could be used in wildlife monitoring, search and rescue, industrial and infrastructure inspection, and many more. Coming to the existing code methods, existing camouflage object techniques could be mainly divided into three sections. Traditional sections, which mainly rely on color and texture analysis, edge detection, pattern matching, and spatial analysis using handcrafted features and rule-based algorithms. However, it yields poor performance in complex scenarios. Second, we have bio-inspired techniques in the literature. These techniques try to mimic human visual system like adaptive visual attention and pattern recognition to enhance object detection. However, these techniques are outperformed by the techniques present in recent literature. Similarly, we have auxiliary information-based techniques. These techniques usually use additional cues such as edges and masks to augment visual data and improve the detection accuracy. Although these techniques yields better performance, however, the proposed technique outperforms state-of-the-art both in terms of accuracy and computational complexity. Here comes the proposed framework. So the proposed framework comprises a backbone that extracts features from the input image at various stages, each characterized by distinct spatial resolution and channel depths. Beginning with the primary features in stage 1, subsequent features undergo channel reduction involving 1-to-1 convolution layers followed by batch normalization and ReLU activation. The mid-level features X2 and X3 undergo a mask function, generating a mask that interacts with the features in the FSM blocks to emphasize background and foreground elements. Following the FSM blocks, features undergo further processing in the context refinement block, involving necessary upscaling, concatenation, and convolution operations. The output of each CRM block feeds into the next one, concurrently supervised with the ground truth at the current stage. Ultimately, a unified loss function guides the network to extract the camouflage objects from the input image. Split and modulation module clearly explained. This module is based on the recently proposed focal modulation, which is considered as a promising alternative to the visual attention mechanism. We use two identical blocks for foreground and background modulations. Features from backbone and mask are interacted, thus forming projection layers. Partitioning the features into query and gating components, projecting them through a series of depth-wise convolution organized in a block structure. The convolution layer's output is consolidated using the gating mechanism, emphasizing specific features. Subsequently, these obtained features interact with the query features, resulting in foreground modulated features as depicted in the figure. The process is reiterated for the background modulation, but in that case we use the negative of the mask features, and the output from both are finally combined for further processing using the context refinement block. Scale and contextual comprehension. The context refinement module operates on a fusion of low and high level features. Initially, high level features undergo upscaling through bilinear operations to align with the spatial dimension of low-level features. After concatenating the combined features, they are divided into 4 subsets. Leveraging skip connection at various levels, convolution layers with varying dilation rates are employed to facilitate a deeper understanding with broader receptive field. Finally, the output of the segmented features is merged with the original features, culminating in the generation of the predicted map, which is represented as P subscript n through a 3 into 3 convolution operation. Effective function of the proposed technique. We have used the combination of binary cross entropy, intersection over union, and dice loss to train our network. The binary cross entropy and IOU losses are computed based on the predictions from the 3 camouflage object masks generated by the Context Refinement Module. Binary cross entropy facilitates pixel-wise classification, where the intersection over union component is pivotal in preserving the structure of the predicted map relative to the ground truth. By introducing a weighting factor to these losses, it enhances their efficacy by assigning varied weights to the class region based on their significance. Similarly, dice loss is used to supervise the mask with respect to the ground truth. The proposed method highlighted in bold consistently surpasses state-of-the-art methods employing various convolution and transformer-based backbones. While there are instances as underlined in blue where the proposed method slightly lags, however, it consistently outperforms in terms of F-score across all the techniques. Simulation study to verify the effectiveness of the modules used in the proposed framework. Given that the baseline solely comprises the output of the backbone followed by 1-into-1 convolutions and a sigmoid function, the results are less than promising. Nevertheless, the incorporation of the FSM module leads to a substantial enhancement in overall results across all evaluation metrics. Similarly, extending the technique with the CRM results in further performance gains, as depicted in the table. The notable improvements stemming from the addition of these modules underscore their effectiveness. Are the visual results of the proposed method compared to the other state-of-the-art approaches? It is evident that the proposed method consistently outperforms, yielding results closer to the ground truth. Notably, in the first row, the method achieves much closer results to the ground truth compared to the other techniques. Presented here are results on the most challenging images containing very small objects from the testing sets. It is evident from the figure that the proposed technique achieves results closer to the ground truth even on the most challenging images with small objects, outperforming state-of-the-art techniques. The performance of the proposed method with various backbones in comparison with other techniques employ the same backbone. Notably, in ResNet-based backbones, our proposed technique, highlighted in blue, performs commendably well, leveraging a more efficient use of parameters. Likewise, with efficient NAC backbones, highlighted in green, our method outperforms state-of-the-art approaches while employing fewer parameters. Similarly, for the transformer-based backbone, our proposed techniques, as shown in red, excels against the state-of-the-art, showcasing superior performance with fewer parameters. We conclude this presentation. Thank you very much for watching the video.